Okay. Well, I guess we can start. It's a pleasure that the ITAMP special seminar is back. Our last seminar was almost half a year ago now on March 12th. And whoever hasn't been to these seminars, they have a very formal, informal format, really, like and we value an informal discussions throughout the talk and after it. Normally, to those who have been there, we also have pizza. That's unfortunately not, like, we can't have pizza now. But we're very, very happy to bring this format online. And this online format also allows us to invite people from across the US and Europe. And yeah, today it's our pleasure to have Dan Stamper-Kurn with us. And maybe also to kind of have this informal character and the personal character that this item seminar normally has. It would be nice if people switch on their cameras so that we can see each other also. Okay, so let me introduce Dan. He did his undergrads at Berkeley and then was a graduate student at MIT, so locally, with Wolfgang Ketteler working on the first alkali gas species then, before moving to a postdoc at Caltech and becoming then faculty at UC Berkeley. Dan has received a number of prizes. Maybe let me just name two: the APS Division for Atomic, Optical, and Molecular Physics Prize for an outstanding thesis, and the Presidential Young Investigator Award in Science and Engineering in 2002. So today we'll hear about his latest work on transport in ultracold atomic materials, a study of flat bands and a window into full counting statistics. Dan.
Okay, thanks. Thanks for inviting me. I didn't know I'd be inaugurating the return of your series, so hopefully this will go well. And then in terms of being at ITAMP and being back at ITAMP, I saw that Wolfgang Ketterle is online, so I hope he doesn't mind that I remind people that it was a couple of nights ago on September 29th that we celebrated the 25th anniversary of achieving Bose condensation in a gas of sodium. That was, for me, that was actually just my first year of working in Wolfgang's lab. So I think that night I was probably at home doing problem sets or something. I wasn't actually in the lab. I came in the next morning, everybody was breathlessly exciting and also bleary-eyed. So I knew something had happened, but it's remarkable to me what a ride it's been for the last 25 years of being a physicist working in this field. Okay, so I'm going to give a talk that describes a couple of recent results from my group, actually on two different experimental projects, and with the hope of inspiring some discussion and maybe getting you guys to provide me some ideas and some advice on where to go next. And I'm loosely stitching them together under the topic of transport. So here's sort of one slide, at least, to try to glue two disparate topics together. In material science, one is often interested in studying transport phenomena. That's one of the fundamental things that we use materials for. We want to understand how that occurs. It also gives us insight on the nature of the materials involved. So actually, one of my early loves in physics was mesoscopic electronics. And so I always go back to thinking about mesoscopic physics experiments or mesoscopic electronics experiments. Here, for example, is an image that was of a device that was used to study the Kondo effect in a sort of a molecular quantum dot setup. And now that we know how to represent materials also through using ultracold atoms, where atoms are the itinerant particles and maybe light is used to create a crystal in which the atoms move, we can ask ourselves whether we also the study of transport phenomena in these artificial materials, maybe to learn about how real materials behave, or maybe just to understand new things about condensed matter physics or many body physics in general. And this is not necessarily a very easy task. So one of the challenges, some of the challenges that come up quite quickly in trying to understand how to do this is that in solid state systems, we have very a different setting than what exists in a cold atom material. For one, if we look at this quantum dot experiment, what's highlighted is of course the structure here, but what's essential to the experiments where they study quantum transport is the fact that there's an infinite reservoir of electrons in this part of the two-dimensional electron gas, and in this part as well. And these electrons, moreover, are thermalized. They're defined by a well-defined temperature and chemical potential. So this is sort of an infinitely open quantum problem where there's just an infinite supply of electrons that can run through and form some kind of steady state current that runs through this mesoscopic structure. That's not really the way in which cold atom materials are presented. We are prepared. We start with a finite reservoir of atoms, and we simply lose them over time. None are ever gained while the experiment continues. So the structure of those experiments is really quite different than in a material transport experiment. Nevertheless, there are certain advantages that we see in cold atom experiments that might actually make the study of transport a very interesting situation and might allow us extra insights. So for one, of course, we know that, whereas in a material science experiment, this is made of a particular, I don't even know what it is, but it's some kind of two-dimensional semiconductor material, and it's not going to change over the course of the experiment. Whereas in a cold atom experiment, we can actually actively change, even within the experiment itself, what type of material the atoms are moving in. And I'll make use of that for some of the experiments where we change lattice potentials as a function of time. That's not something we can do easily in condensed matter systems. A second one is that we can create quantum systems of atoms that are far out of equilibrium. Transport is a non-equilibrium problem, right? This is there's a flow of electrons out of here, so that's not an equilibrium. It's a one-directional flow, not in the other direction. So this is not a study of equilibrium, but even more, cold atoms can be driven even further from equilibrium to study transport in very different scenarios than you could in solid state. And then finally, of course, there's very different ways to study what's going on, and maybe refining our measurement methods and applying them to the study of quantum transport could reveal something very new. So people have caught on to this idea, and there are experiments. These are a couple of images taken out of this review paper down here, where people have rigged up cold atomic systems to start opening up the study of transport phenomena. So there's going to be a lot to understand. There's going to be a lot to uncover in this topic. And my group is making just some very modest entries into this field, and maybe they can be regarded as a study of transport in materials. Okay, so I'll talk about really two separate topics. That's as much as I've stitched them together. The first one is a study of transport in a flat band system and how the band structure in particular is significantly renormalized or modified by the effective interactions between atoms. One of the focuses in my group for a number of years now has been to take on the topic of geometric frustration in materials. And geometric frustration in materials is a rather interesting topic because geometric frustration sort of frustrates a material's ability to do anything simple. So a lot of times we have a material system, it's a quantum many-body system. It sounds like a really complicated system altogether. And yet when we ask what it does at low temperature at equilibrium, it actually resolves into a very simple configuration that can be simply described, like let's say a metal or something in an electronic system. Frustration is a way of sort of precluding that simplification. It sort of tells a material, rather than having one obvious thing to do, actually we're going to present you with many simultaneously appealing phases that you can take on. And then given that, sometimes subtle effects show up and the material actually adopts a phase of matter that is rather complex and one that we want to study. My focus here is going to be on geometric frustration as it applies to orbital effects, or to the effects of motion rather than, let's say, geometric frustration for magnetism. So maybe you can think about situations where motion of atoms can be mapped onto some kind of pseudo magnetic degree of freedom as well. So that's a fine way to think about it. Anyhow, the focus will be on orbital geometric frustration, and specifically, I'll look at the kagome lattice. The kagome lattice is a two-dimensional lattice configuration where triangular plaquettes are joined by their vertices. And this kind of configuration of sites possesses geometric frustration for orbital motion. And one way to exhibit that is to think about the following state. Imagine I take a single particle, I place it in the kagome lattice to where it can hop around to neighboring sites with a certain tunneling energy J. But I put it in an initial state where the particle resides in these 6 states, this hexagonal structure of 6 states that surrounds a site, an empty site within the kagome lattice. And I specify the wave function of this particle so that the phase of the wave function alternates from site to site. And you see that this single particle wave function is stationary. It can't evolve. The particle inhabiting this hexagon can't escape because its motion is frustrated. So let's say we ask whether the particle in this configuration can tunnel out so that it occupies, say, this site. The answer is no, because the probability amplitude to hop on this bond cancels with the probability amplitude to hop on that bond. So orbital motion becomes frustrated. In a macroscopic lattice, two-dimensional lattice, I can imagine such a single particle state occupying each of the different hexagonal structures within the kagome lattice. That means I now have a macroscopic number of single particle states, all of which are eigenstates, they're stationary, all of which have exactly the same energy. So that plethora of states is represented in the band structure of this material by a flat band. So these are all the states, but now represented in momentum space. But these are all of these localized stationary states of atoms that create a band that has basically 0 dispersion. This is a band in which promoting particles to a different momentum state doesn't actually change their kinetic energy. And so there's examples in materials, let's say a heavy fermion materials, where electrons occupy or partly occupy a band that has very little dispersion. And it's under those circumstances that electron-electron interactions can create really interesting phases of matter because kinetic energy doesn't tell them what to do. So that is why this is an interesting experiment for us to study. What we wanted to do was start gaining some information about the band structure of the kagome lattice and do an experiment that would kind of exhibit in a very visceral way the existence of this flat band. So it's actually a very simple project. Let's see if we can characterize the band structure of a kagome lattice and show that its third band, so here's the first band, the second band, and the third band of the kagome lattice, let's show that its third band is flat. By the way, there is also another lattice configuration that's been used in cold atom experiments, something called the Lieb lattice, which also contains a flat band. The flat band of the Lieb lattice can also be associated with a localized state from which particles cannot tunnel because of destructive interference. In the case of the Lieb lattice, the flat band is the second band of the lattice. In the case of the kagome lattice, it's the third band. The Lieb and kagome lattices are similar in that they both have a unit cell with 3 sites, but there's obviously some differences. The roles of flat bands in material systems, again, have been thought about deeply in the context of condensed matter physics. So for example, this paper, which is the source of these images over here, discusses how flat bands could be deformed due to interactions between particles. That's actually going to be a topic that I'll get to, our experiments will show. And then there's also been some experimental work specifically on the Lieb lattice, which also studied, looked for whether the flat band in the Lieb lattice is indeed flat. So these are some precedents to our work. The way, I'll just flash this up, maybe people are already familiar, but the way in which we create a kagome lattice in our setup is by overlapping two triangular lattices in 2 dimensions. The 2 triangular lattices are formed with light that has 2 different wavelengths that have a 2-to-1 wavelength ratio. The positions of the interference patterns, the optical lattices produced by the green light and by the infrared light, these positions are stabilized interferometrically. So when we turn on these 2 triangular lattices, let's say ramp them up at the same time, we place this kagome lattice onto the atoms that at this point is what I would call a lattice of tubes. So within the horizontal plane in our apparatus, the atoms occupy the sites of a kagome lattice, but in the 3rd dimension, there's very little confinement. So particularly for this experiment, that's the configuration in which we worked. And I'll just mention that of late, our experiment has become more stable by the fact that we're now generating the 532 nanometer light as a direct harmonic generation from the base light, which is at 1064 nanometers. That's given us a lot of extra stability in the experiment that we're making use of. Okay, so now the question is, how do we study the band structure of this kagome lattice? And we're going to make use of a really simple principle from condensed matter physics. So let me show it first here in the, I guess this is the extended zone scheme of materials. So think about a particle moving just in 1 dimension. In the absence of any lattice potential that's imposed upon it, the dispersion relation of that particle is simply parabolic. So the eigenstates of the particle are momentum eigenstates, and their energy is simply the kinetic energy of a particle moving freely. Now, when we add a lattice potential, let's imagine we add this lattice potential just adiabatically, starting from 0, and we ramp it up to some non-zero value. And you can see it's really clearly exhibited in this image over here. There's going to be a direct mapping, an adiabatic mapping from the momentum states in the absence of a lattice to the band states that exist in the presence of a lattice. And this fact gives us a way of placing atoms in band structure at a quasi-momentum of choice and at a band index of choice. So now I'll turn over to this graph over here, which shows the same physics as what's shown over here, but in the repeated zone picture. So if I take a particle in the absence of any lattice potential, it's quite easy for me to put a force on it and accelerate it to where it's moving at some non-zero momentum. Let's say that non-zero momentum exists within this range of momentum. And now if I adiabatically ramp on the lattice potential, I would expect this state, which is the kinetic energy, it's a simple momentum state of atoms, to map onto this state, which is a block state inside of the lattice. And because I've accelerated atoms to a particular place within momentum space, I will place them specifically in a particular band. So if I accelerate them to this momentum, they'll be adiabatically mapped into the 2nd band of the lattice. Or if I accelerated them this far, they'd be adiabatically mapped into the 3rd band. So that's the method in which we are going to place atoms within the band structure of our kagome lattice. The kagome lattice, again, has this configuration. It's a lattice where there's a unit cell that has, here's the unit cell drawn, a unit cell that has 3 sites in it that are at equal energy. There's a 4th site here that is excluded from consideration by being very high in energy. This here is the Brillouin zone map for a triangular lattice in 2 dimensions. And in our experiments, this is how we're going to proceed. We start with a Bose condensate of rubidium atoms with a variable number and a variable density. That'll be relevant later on. And then we simply push them in the absence of any lattice potential. This pushing is done by turning on a red detuned light beam that puts on an optical dipole force and pushes the atoms in an impulsive manner. And specifically, we accelerate the atoms up along this axis, which I'll call the y-axis. And depending on how long I keep this pushing beam on, or what intensity it has, I can push them to any value of the momentum along this axis. And you see, if I push them by a small amount, then when I adiabatically thereafter ramp on the lattice, the atoms will map onto the ground band of the kagome lattice at a variable momentum that's shown in this trajectory over here. If I push hard enough, the atoms will skip over a band crossing, and now they'll be placed in a region where they would adiabatically map onto the third band of the kagome lattice, which is the one that we want to focus on. If I push even further, then we can place atoms in an initial state which adiabatically would actually map onto the fourth band of the kagome lattice. That fourth band is a band that mostly resides at this D site within the lattice. So here's the outcome of that experiment. So again, I'm showing you characteristic images that we obtain for atoms at rest, atoms accelerated, but where they're going to be adiabatically mapped onto the first band, atoms that would be mapped onto the third band, and also atoms that would be mapped onto the fourth band of the kagome lattice. And we characterize these states by imaging them in velocity space. So the experiment is done as follows. We push the atoms, we ramp up this lattice of tubes, and then after a very short while, we release the atoms from the optical trap altogether. And after some time, their position reflects the momentum that they had while they were trapped inside of the lattice. So this image that we take is basically a velocity space image of the block state of atoms in this kagome lattice. So here I compare the images that we see to what we would predict based on just single particle calculations that entirely neglect interaction effects. And you see that there's a pretty close qualitative resemblance between the maps in momentum space that we see for cold atoms in our experiments and the maps that we see that is predicted by band theory. So it seems like we've done our experiment right, and indeed we're able to place atoms entirely within a block state in some excited band of the kagome lattice. But we can do better than that as well. So this is a result that comes out, let's say, from the Hellman-Feynman theorem. It's also just something commonly known in condensed matter physics. You can calculate the group velocity. The group velocity is a property of band structure. Locally, it's the gradient of the band structure at any location within band structure. And it turns out that the group velocity is identical to the average velocity of the block state. That comes out of this theorem. So the group velocity is easy to measure directly from these images. All I need to do is understand how the atoms are distributed in this momentum space picture, take the average momentum, and then I get the group velocity directly. I don't actually have to calculate gradients. I don't have to measure the energy of the band structure at several locations. All I need to do is measure the average velocity in the block state. The group velocity tells us about the dispersion of a band, right? So if a band has large dispersion, this gradient will be large, the group velocity will be large. And if it has very small dispersion, then this gradient would be very small, and the group velocity should be very small. In fact, if I calculate for a non-interacting band structure, so just single particle band structure in this particular optical kagome lattice, I would predict the group velocity that's given by this dashed line. And of course, the group velocity within the third band of the kagome lattice is very small, or is predicted to be very small, because this is a band that's supposed to be very flat. But in fact, our data are quite convincingly showing us that the group velocity is not small within the flat band, within the nominally flat band of the kagome lattice. In fact, that velocity is quite modified. It's quite different than we expect based on single particle physics. So that's kind of the big result of this paper. Now, it took a lot of head scratching to figure out what was going on here. We suspected mostly it was just technical problems with the experiment. But then everything seemed to check out. We thought about it a little more clearly, and we realized that this is actually an effect that we could have predicted and could have expected. And the effect is that interactions between the atoms change the structure of the lattice. And because of that, they change the band structure of the lattice. In condensed matter physics, this effect is known as the renormalization of band structure due to the interactions, let's say, between electrons. In condensed matter physics, we also have a problem where we might rely on single particle band structure within a lattice, but then we have to realize that the electrons that inhabit that lattice are all interacting with one another. So the effective band structure in the lattice can be pretty different from what we expect in the absence of interactions. That turns out to be really what is leading the process here as well. So for example, if I look at, in particular at this point in the flat band, the one that we looked at most closely, I can calculate the velocity space distribution. Let's say this is what's expected for non-interacting atoms. But I can also calculate the real space distribution of atoms in this particular block state. That's easy to calculate. And you end up with a picture that looks kind of like this. So here's the unit cell of the kagome lattice. Here are 3 sites of the kagome lattice, A, B, C, where the optical potential is low and equal. So these are the 3 low energy sites of the kagome lattice. But for this particular block state, where the atoms are accelerated to a particular quasi-momentum and placed into the third band, the distribution of atoms within the unit cell does not have the same symmetry as the kagome lattice itself. Not surprising, right? Because we no longer have the same symmetry. We've pushed the atoms to a non-zero quasi-momentum that breaks the C3 symmetry of the kagome lattice. It's not surprising that the block state would also break that C3 symmetry. And it certainly does, in a way where the atoms primarily occupy 2 sites of the kagome lattice and not so much the third side of the kagome lattice. Now we think, aha, the atoms repel one another. So in a mean field picture, the atoms increase the energy due to interactions at 2 sites of the kagome lattice and compared to the third site of the kagome lattice. And now the atoms inhabit a lattice which is not a kagome lattice. It doesn't have C3 symmetry. It no longer has these bound stationary states. It should no longer have a dispersion relation that is flat in the third band. And that's exactly what we end up seeing. So what we're studying is sort of a non-linear version of the block band theory, where you have to consider also the interactions between atoms as part of the lattice potential. And non-linear block band theory has some pretty surprising outcomes. I'll talk about them a little bit in terms of our future outlook. But one of the outcomes is that the band structure of the lattice is modified significantly. This experiment has a lesson to teach us. So one of the scenarios that I'm very much looking forward to studying, but we're not studying yet in this experiment, is what happens when you take a bunch of interacting bosons and you ask them to come to equilibrium in a flat band. So, if we were to try to realize that experimentally, I would have to learn how to flip the band structure of the kagome lattice and make the flat band of the kagome lattice the ground band. Or perhaps I can do what I've done here, which is launch the atoms into the excited flat band of the kagome lattice and hope for some reason that the atoms will equilibrate within that flat band in some transient manner and mimic what would happen if they were truly equilibrating in the ground state. Anyhow, people have considered what would happen if I had one of these inverted kagome lattices with a band where the flat band is the ground band. What would be the nature of many bosons in that situation? So there's a great paper by Huber and Altman that suggests that there's sort of a 3-step scenario in that particular configuration. At very low fillings, so very few bosons within the bands, they predict that the bosons would crystallize. And this makes sense. We have these stationary states, these hexagonal states that I talked about at the beginning. And if I can localize atoms in a few of those different hexagons, they never interact with one another. So that should be a stable configuration. And you can fill those states up to a certain filling before interactions kind of are forced upon you. When those interactions are forced upon you, the prediction is that the system becomes super solid. The Wigner crystal is maintained, but extra bosons ride within the band structure that's created by this Wigner crystal, and they bose condense within it. At much higher density, the prediction is that the atoms would simply dissolve into a superfluid altogether. And it's in that setting that this other paper by Hui Xi's group is probably relevant, where what they've considered is the problem essentially that we're studying is what would happen under mean field interactions if you put many atoms in their case, the flat band, the flat ground band of the kagome lattice. And what they predict is that the interactions between atoms will cause this flat band structure to no longer be flat. And if all the atoms are placed in particular locations within the band structure, then they will create self-consistently a band structure that stabilizes the superfluid and gives energy to the excitations on top of the superfluid. So if you will, our experiment on renormalization of band structure in the Kagome lattice is really sort of proving this concept, that the flat band will be distorted by the presence of interactions. We're not in a position to study the thermalization of bosons in this flat band yet. So just to conclude this first half of the presentation, we've managed to place atoms within the flat band of the Kagome lattice, something we've wanted to do for a long time. And we've started to characterize their state. We see that interactions between the atoms cause the flat band no longer to be flat. Unfortunately, we're unable to study this very non-equilibrium excited state of our system with all atoms placed in the third band of the Kagome lattice. We're unable to study it for a long period of time. It turns out that within hundreds of microseconds, interactions cause the atoms to rain down into the lower bands of the band structure. We think that this is happening because we're working in this lattice of tubes configuration where atoms can relax their band state by just dumping energy into the third dimension that is unconfined. So we intend to start up this experiment again, adding a vertical lattice, in that third dimension that would divide into isolated planes and cut off this escape route. But in the meanwhile, I think we've touched on what could be a pretty rich vein of study, which is studying nonlinear band structure effects. And in particular, it makes you wonder whether band geometry effects, which have been the focus of a lot of studies in cold atom experiments, how they are going to fare when you also add interactions that make the problems nonlinear. So let me just say a couple of words about that. We're familiar with linear band touching points. So like in graphene, this is a situation that's studied ad nauseum in condensed matter physics. But you have situations where you have these Dirac touching points between two bands. And a lot of really interesting physics comes out from that Dirac point. This is a point where the bands cross each other linearly. In the vicinity of this linear touching point, I can understand the Bloch states and the behavior of electrons near there by considering a pseudo-spin degree of freedom. So in particular, I can consider, let's say, spin up to be electrons located at one site of the site within the unit cell, and B being where the particles are located, spin down being particles located in the other side of the unit cell. And in the vicinity of this linear touching point, if I look at the Hamiltonian of the system in this pseudo-spin basis, I see that it's equivalent to a spin 1/2 particle placed in a magnetic field, where the magnetic field is, let's say, points radially outward, depending on how you're displaced from the Dirac point in momentum space. And this leads to all sorts of interesting effects. For example, the fact that if I adiabatically drag a particle around the Dirac point, I pick up a phase of pi because I've taken a spin 1/2 particle and rotated it around the Bloch sphere. Equally interesting is the situation of a quadratic touching point in band structure. And in the band structure of our Kagome lattice, that's exactly what occurs. So here's the top band, the third band of the Kagome lattice. And we've studied its dispersion right at this point between the K and M points of the band structure. But with some modifications of our experiment, we should be able to push the atoms over to the gamma point. And at the gamma point, the third band actually touches the second band of the lattice. The touching is a quadratic point. The two energies approach each other quadratically rather than linear. We can similarly understand this quadratic touching point by appealing to a pseudo-spin degree of freedom. So at the gamma point, we've restored the C3 symmetry of our problem. And if I think about the states within the unit cell that have different eigenvalues under the C3 rotation operator, I find that there's a state which has eigenvalue 0, so it has the same phase at sites A, B, and C. That's the state that corresponds to the ground state here. And then there's two other states, called these chiral states, where within, let's say, these upward pointing plaquettes, the states of a particle are either circulating in one way or circulating in the other way. You can regard these as chiral states or maybe as orbital magnetic states of a particle. And these two states are degenerate at the gamma point. I can regard them as, say, as pseudo-spin up and down. And then the states, when I move away from the gamma point, can be thought of as simply superpositions of these two states. The Hamiltonian, in this case, near the quadratic touching point, looks like this. It's like a spin 1/2 particle in a magnetic field. But now as we go around the band touching point, because this is a linear and not quadratic touching point, the magnetic field wraps around twice as I go around the touching point. And this has interesting impacts on all sorts of problems. There was a recent paper that discussed what happens to Landau levels if you take a system where at the quadratic touching point, you put it in a magnetic field and you look for a Hall effect kind of physics. So the quadratic touching point is going to be an interesting thing for us to study in our cold atomic systems. But one point is kind of curious. If I look at these two states which are degenerate at the gamma point, the different helicities of motion, the different chiral states, I could recombine them also into a superposition state. Let's say this superposition state, which looks kind of like a PZ orbital in chemistry, or this superposition state, which looks kind of like a PX orbital in chemistry. And reduced to just the 3 states of the kagome lattice, this is what the real wave functions would look like with this combination and with that combination. Nominally, for non-interacting, for linear quantum mechanics, the fact that these are states with equal energy at the gamma point means that these are also states with equal energy and all at the same energy at that same gamma point. But now when you add repulsive interactions, it becomes clear that these are not states of equal energy, right? When we have these chiral states, we have atoms distributed at 3 sites so that the density of atoms at any one site is kind of low. But if I look at these superposition states, I see that the density of atoms is starting to build up in particular sites. And the interaction energy for this state is going to be higher than for the orbital states, for the chiral states. And for this one, even more so. So this PZ orbital will be a very high energy state under interactions. This PX orbital will be somewhat lower, and these will be lower still. Plus, let's recall that at the gamma point, we still have C3 symmetry. So if this is an eigenstate of my system, then so is this, and so is this. But these eigenstates are not at the same energy as, let's say, these 3 eigenstates. And so what's happened to band structure is that the number of states at this quadratic band touching has proliferated enormously, from being just 2 states to now being at least 8 states, and from being degenerate to being non-degenerate. We've done a little bit of calculation of this problem, only a partial calculation. I'm a little embarrassed to show this, but we do identify in the complete band structure the presence of these real valued eigenstates. In some other calculations, we now also have found these chiral states over here. So overall, studying this kind of nonlinear band structure and maybe going back to try to see geometric effects of the band structure is going to be an interesting thing for us to study. Okay, that's the end of this part. I'm going to go on because I feel like I took a little bit too long. So maybe I'll ask everybody, how do you want to handle it? Do you want to have people ask questions now, or?
If you feel like it works best with the time that you first continue, we can take the questions at the end, like whatever you prefer.
Okay, let's just keep going.
Okay.
Now I want to talk about a second experiment in my lab, which makes use of a setup where we have atoms placed within an optical cavity. And this is a setup that we've used for many experiments in the past, but here we're going to use it in particular to develop a very sensitive sensor that can allow us to study a quantum gas that lives within a high finesse cavity. So we're just using it as a very sensitive optical measurement device and thinking about what new science can we uncover by applying that device to our system. Experimentally, again, you've probably seen this already, but we make use of an atom chip that grabs rubidium atoms and places them at a location where the atoms are trapped within a high finesse optical resonator. And in particular, we can use this magnetic trap to place them in a single site of an optical lattice that is supported by this resonator structure. And then we're going to use that same cavity in which the atoms are trapped. We're also going to use its cavity modes to probe the atoms that live within there. And this is the principle we're going to use. So we have atoms, many atoms trapped within one specific location. It's actually a two-dimensional pancake, two-dimensional pancake within the three-dimensional optical cavity. And when we interrogate this cavity with light that is near resonant with the rubidium atoms inside of that cavity, what we note is that the presence of these rubidium atoms shifts the resonance frequency of the cavity due to dispersive effects. And that shift is additive. So if I put more and more atoms in here, I end up with a shift in the cavity resonance that is proportional to the number of atoms inside of the cavity. And we're going to use this property alone in order to study our quantum gas. We're going to make precise and continuous measurements. We're going to count the number of atoms inside of a gas of atoms. And in particular, we're going to count that number while that number is changing. And we're going to change it by affecting evaporative cooling. So atoms are trapped within an optical lattice potential. The focus of the beam within the cavity is Gaussian, so there's a Gaussian potential. But on top of that, we apply a gradient of the magnetic field, which is now able to affect evaporation, where the hot atoms inside of this volume can collide and escape from the cavity. And we now monitor that process in real time. So let's say I will only measure the resonance frequency of my cavity. I will only measure the transfer of light at a particular frequency through the cavity. As the cavity resonance changes, here's the cavity resonance frequency right now, as that cavity resonance frequency changes, because atoms are lost from the trap. So something like this occurs. As the atoms are lost, the resonance frequency of the cavity shifts as a function of time. And because of that, let's say the intensity of light that transfers through the cavity varies as a function of time. First, it increases, later it decreases. But in any case, I can analyze the shape of this curve and its temporal evolution in order to get a measurement in real time of how many atoms are still inside of the optical lattice. This was an early attempt to do it. Now we've actually improved our method quite a lot. We use continuous feedback, so we send light through the optical cavity system. We measure the intensity of light going through the cavity, and we stabilize that light so it's, let's say, halfway up the transmission curve running through the cavity. We use some active feedback to keep changing the frequency of the light to remain on resonance. And the signal that drives that feedback is then a direct of the number of atoms inside of the cavity. Here's one trace, for example, of the number of atoms inside of a cavity during a 300 millisecond long experiment where the atoms are slowly expelled due to evaporative cooling. We can repeat this experiment with different measurement strengths, which should give us different levels of precision on on counting the atoms. Also, incidentally, the measurement process disturbs the atoms. So as we increase the light level, we also study evaporative cooling in a system that is being driven by ever more heating from spontaneous variations in the intensity of light inside of the cavity. So here's, let's say, the record of the atom number inside of our cavity as a function of time while the atoms are being interrogated by just a few picowatts of light. And we start off with many atoms in this two-dimensional pancake, and then through evaporative cooling, that number drops. The experiment is pretty stable, so we can repeat this experiment several hundred times at each of these settings. And with that information, we can now start looking at temporal correlations. So in cold atom experiments, we've for a long time wanted to study two-point or two-time correlations within a quantum gas. Here's an example of our doing exactly that. So for example, I can look at these measurement records and I can compare the atom number, the counting measurement, at an early time, let's say time 0, to a later time, either a later time that's soon after the initial time, or a later time that's very far after the initial time. And I can do a very simple thing, which is try to look at correlations between these two number measurements. Not surprising, if the two times are spaced by a small interval, then the measurements are very strongly correlated. That's because we're measuring the same atom number essentially twice. But if we wait a long time, then we lose correlations between the two measurements because a lot of sources of fluctuations have come into play since this early time, by the time that we're looking at a much smaller number of atoms. So in fact, we have a lot of information in this measurement record. We have a continuous measurement of the atom number, but we're only using that for a very limited analysis, which is to look at two-time correlations. And with that two-time correlation, we're interested in studying, as an example, studying the dynamics of evaporative cooling. So again, in evaporative cooling, you have a trapping volume, and then collisions between atoms can promote some atoms to high energy, and they can escape over some kind of threshold in the trap depth and leave the trap. And there have been attempts to describe evaporative cooling as sort of a non-equilibrium thermodynamic process. It obviously has to do with thermodynamics because of the density, temperature, collision rate, everything of the gas that is inside of this volume is what drives the evaporation rate. So we are interested in this experiment to see if we can do some precise measurements and confirm pictures that have been put forward for what is the predicted average rate of evaporative cooling, but also because we can measure individual realizations of evaporative cooling one after the other, what is predicted for the variations in the evaporative cooling rate. So let me present a couple of analyses of this and then I'll conclude. We're interested in, let's say, studying the evolution of the average number of atoms that is left behind in a gas after it's undergone evaporative cooling. So we consider, let's say, evaporation from one early time to a late time. The number at early time is given by N1. The number at late time is given by N2. The theory of evaporative cooling should define this function. It should tell me, given a certain number of atoms at an early time, what is expected for the number of atoms at a late time. That's something I can demand of the theory. Now, just looking at this equation here, I can define two quantities. One is, if I simply take the ratio of the number of atoms at late times to the number of atoms at early times, I have something like the survival probability, or the remaining fraction of atoms inside of the gas. Another dimensionless quantity I can consider is a derivative. So I want to understand, how does the number of atoms we see at late times vary with the number of atoms that we see at early times? Let me call that derivative A. It's interesting to examine the difference between these two quantities. If this quantity A is the same as P, then I would say that what we have here is a linear process. The number of atoms at late times varies linearly and proportionally to the number of atoms at early times. In that case, this derivative will be simply equal to the remaining fraction. Or there could be nonlinearities in the evaporative cooling process that lead to either super or sublinear evolution. By superlinear, I mean a situation where if I vary the initial atom number by a small amount, I actually vary the final atom number by a very large amount. So small fluctuations in the initial state are amplified to be very large variations in the final state. That would be observed by this quantity A minus P being greater than 0. And then similarly, evaporative cooling might be described as a sublinear process, where even if I have variations in the initial atom number, I end up with a final atom number that is very tightly constrained. So we examine this quantity A minus P for the data shown over here from different starting points of the experiment. And we plot A minus P as a function of the number of atoms that remain at times after this initial time. And you see that our data actually show two different regimes. We see some regime where the evolution I would call superlinear. Small variations in the initial atom number actually lead to very large changes in the final atom number if we start at early times. And the way we understand that now is that at early times in the experiment, the state of the gas is not entirely determined by the atom number. We also have to know the temperature of the atoms inside of the trap. And it turns out that there's a correlation between the initial temperature of the gas and the initial atom number of the gas. If the atoms enter evaporative cooling in a hotter state, then more atoms are lost. And if the atoms enter in a a colder state, then at a certain point, fewer atoms are lost. And so that sort of hidden variable is driving, because of its correlation with the atom number, is driving this behavior. By the time evaporative cooling has been forced long enough, that temperature variation goes away. And at this point in time, for example, all of our samples should have arrived to the same temperature. They should only vary in their atom number. And now we see what I would call is sort of more the native thermodynamics of evaporative cooling, which is that at a native level, it's sublinear. Even variations of the initial atom number become suppressed through evaporative cooling. And that's what's shown here with this quantity A minus P going negative. I can also examine evaporative cooling in terms of fluctuations, not just the evolution of average properties, but how fluctuations themselves might grow over time. So now I'm thinking about evaporative cooling as follows. At a certain point after, let's say I've evaporatively cooled for a time and now I stop. My gas is divided into two populations. There's the atoms that remain and the atoms that have evaporated away. And I can consider whether this under identical starting conditions, like beyond anything that is due to variations in the initial conditions, will the number of atoms that remain fluctuate? And the answer is, well, likely to be yes. Well, for one, there's measurement noise. So my measurement of the number of atoms at late times will vary just because of measurement noise. So that's a somewhat uninteresting fluctuation in our system. But beyond that, there would be fluctuations that have to do with physical changes in the system itself. So for example, let's imagine that evaporative cooling is simply a binomial process. It's like coin flipping. At a certain point of time, I just ask each atom individually with a certain probability, are you going to stay or are you going to go? And that would result in fluctuations that are described by the binomial distribution, where there's going to be a variance in the number of atoms that remain in the trap as a function of the remaining fraction. And this is a description of the variance in the binomial distribution. Or maybe I'll have fluctuations that are even larger than this. So for example, if during evaporative cooling, atoms don't escape one by one, but let's say they escape 5 by 5 in bunches, then I would expect this binomial distribution to have a much larger variance because each event leads to a very large variation in atom number. Or maybe there's some other processes. So for example, we talked about how evaporative cooling can either suppress variations in atom number as a sublinear process, or maybe can amplify them as a superlinear process. And that effect doesn't just act on the average number of atoms, but it also acts on the fluctuations that are generated during evaporative cooling. So that is also an effect that I can look for in studying these fluctuations. Or maybe this is a thermodynamics question. Imagine if, different than this picture over here, I introduced my atoms into a potential that had a deep trap volume and then a very large shelf that doesn't dip off here, but a very, very large shelf into which atoms can sort of evaporate. Rarely they'll also come back as well. Now I'm able to treat evaporative cooling as actually an equilibrium problem. I can ask, in that equilibrium situation of a potential that is, has this variation of potential energy with position, what's the variation of the number of atoms that I expect in a small volume within this large thermodynamic system? And that is something that is calculable either in the canonical or the grand canonical treatment. And you find a variance in the atom number according to these statistical theories, which is related to the temperature, but also the compressibility of the gas. So maybe studying these fluctuations is the same as studying thermodynamic properties of the gas. Or maybe I should really think of this as like a transport problem. I should think of this almost like a quantum dot experiment where people have done things like do full counting statistics of atoms on a quantum dot. And there's going to be something generic and beautiful from the theory of quantum transport that should describe this experiment. I'm putting these all out as suggestions to you because I don't actually know fully how to analyze what we're observing. And this is what we observe. So I'll focus actually on this lower graph, where we try to study this natural or native behavior of evaporative cooling by looking at early times where, let's say halfway within the experiment, where the initial temperature fluctuations have been ironed out. And now we're just studying the growth of fluctuations in time from that point forward. And we're comparing the additional variance that we see in this quantity N2 beyond what is explained by its correlation with N1. And theoretically, I'm comparing our data to a sum of two terms. One is this dashed line, which describes how much measurement noise should create additional fluctuations in N2. And then added upon that is the binomial prediction. And you see here's data for the different measurement intensities in our experiment. You see that the data are roughly in agreement with additional fluctuations in the quantity N2 being explained by the sum of measurement noise and binomial noise. We certainly see a lack of fluctuations that is very much larger than binomial noise. I can't rule out that native evaporative cooling would create a noise that is lower than binomial noise, because maybe our experiments are obscured by some other source of noise. But at least I know that evaporative cooling is not leading to a growth of fluctuations that is much larger than binomial. Okay, so we're also thinking about using this real-time measurement as a way of actually controlling evaporative cooling using active feedback. So rather than just watching it passively, we can, let's say, let evaporative cooling go on for a while and then stop at some location and try to stabilize, let's say, the atom number at that location. We have evidence that this works, but we're still trying to get a more refined understanding of this to where we can, at least in a practical sense, we can create atomic samples over and over again that are very identical in their conditions. And this can be useful for future experiments. So now I want to bring this part of the experiment to a close, of the description to a close. What is really going to be most interesting is connecting these two pieces of what I taught you, or what I told you about. Creating an experiment where you can clearly study a quantum transport phenomenon. I wouldn't call evaporative cooling a quantum transport phenomenon, it's rather classical, but maybe we can push in a direction where we're really studying something that's very quantum in the sense of kind of mesoscopic electronics. And then we can make these precise measurements of not just atom number, but either multi-time correlations, or maybe now I know to call this full counting statistics under some quantum transport system. We are very interested in understanding systems that are acted upon by measurement-based feedback. I gave you a glimpse of that with our attempt to stabilize the atom number. In parallel, and this should be interesting to the M part of ITAMP, we're also actively now in the lab kind of changing direction, and we're starting to try to make use of the fact that we can drive photoassociation transitions between atoms that are trapped in our optical cavity. And maybe for the first time, start studying the effects of single photon, single molecule cavity QED in this kind of setting. And a particularly nice idea that I like is the idea of using the vacuum fluctuations of the cavity as a catalyst. So if we think about photoassociation as a photochemical process, where a pair of atoms absorb a photon and then can go into many final molecular states through spontaneous emission, maybe I can direct this chemical process from initial state to final state toward a specific final state by using the cavity to enhance emission into one particular final state of the molecule. So that's something that we're working toward, and it's actually going quite well now. And then hopefully soon we'll start having results about a new experiment that we've been building for quite some time. And there, the specialization that we're developing is the ability to trap atoms in optical tweezers inside of a high-finesse optical cavity, either to use cavity-based interactions to get atoms in different tweezers to interact with one another, but also to use the cavity as a very fast measurement device. And this is relevant to the folks, let's say at Harvard, that are working with these tweezer array experiments, where they really would like to find a way to speed up the rate at which they're measuring their tweezer system. And this would be kind of a prototype system to show that wrapping your tweezer experiment inside of a cavity is one way to go. Okay, so I will finish. I didn't tell you about experiments that I think are really interesting, where we study heteronuclear spinor gases of two different elements of atoms. I didn't tell you about our efforts to start laser cooling a new set of atoms, starting with titanium. I didn't tell you about my activities regarding opportunities for quantum gas experiments in space. And I didn't tell you about what is my greatest time sink at present, which is this newly founded Challenge Institute for Quantum Computation, of which I'm apparently the institute director. But anyhow, here's my group, and I want to point out the people that worked on the lattice part of the experiment are Zephy, and then this team of Charles, Malta, Shawen, and then a visiting student, Govind, who has since gone back to Innsbruck. And then the people working on the cavity experiments are here shown in gray, with Johannes and Julian currently, and Josh leading the current efforts on, let's say, a photochemistry inside of a cavity. And then Justin and Emma, let's see, Alec and Rachel have kind of other undergrads that have moved on, but others at present that are building up this new cavity experiment. So that's it. Thanks a lot.
Wow, thank you very much for this very nice talk with 2 parts. I guess there must be lots of questions. I have some, but maybe we can try to just open the microphone and let people speak.
Great. People could ask. Yeah.
Well, maybe I can start with the first question. Like on the second part, you were talking about the prospect of maybe putting like atoms, like combining atoms into molecules. Is there also like any way of like making them just interact, like in a simple way, just like a dispersive interaction without like molecule formation? Or are they even like, maybe do you already see signatures of some like not single particle loss processes, maybe 2 particle or 3 particle losses?
Okay, so the atoms in our cavity certainly interact with one another. So I guess our evaporative cooling measurements are characterizing that. It's interesting to think about whether we can just use light in the cavity to, let's say, enhance or tune their interactions. Not something that we've tried to do very, very deeply. We have thought about, driving photodissociation, right, would cause enhanced losses for pairs of atoms, and actually both in the existing experiment, but also certainly in this new tweezer experiment. That's one of the things we'd like to resolve in time. This presumed dynamic where in an optical tweezer you can trap n atoms, and then when you have them interact with near resonant light, the atoms are ejected in pairs. That's something that we should be able to resolve in real time. Something we'd like to attempt to do. That's a partial answer to your question, but what more were you interested in?
Well, I mean, like, do you already see any signatures of pair loss or 3 particle loss? I guess that's maybe I missed it, or maybe that's also difficult to extract from the data.
In the evaporative cooling work, we do not see signatures of multi-particle loss.
Yeah.
That would have shown up in, let's say, these enhanced fluctuations, and that's not what we see, right? So that's not the dominant source of atom loss in that particular setup. But yeah, turn on. Well, Feshbach resonances are hard to reach, but turn on. We slow down evaporative cooling. There should be significant 3-body losses. So if we slow down the evaporative cooling loss, maybe we can see the 3 particle losses as the dominant loss mechanism. That's one possibility. Or again, we can maybe enhance things with near resonant light.
Let me ask something about evaporative cooling. We know that for evaporative cooling in certain traps, there is a threshold for runaway evaporation. If you put in enough atoms initially, you will actually come to a situation that during evaporation, density and collision rate will build up and you have accelerated evaporation, which gets more and more efficient. But if your atom number is below the threshold for runaway evaporation, evaporation will get slower and slower and slower and more lossy. So how would this transition from slow down evaporation to runaway evaporation, from very inefficient to very efficient evaporation, show up in your correlation measurement?
Yeah, great question. So I think it would show up both in the study of these averages. If I study this quantity G, which relates the initial atom number to the final atom number to the initial atom number, there should be a kink in that function when you pass this threshold. So for example, you might find that if the atom number is low enough, then the final atom number will be really low because the atoms always remain at a very high temperature. Whereas if the atom number is higher and the temperature then is dropped, I think that we would see this shrinking of the final atom number because of how the runaway process ends up sort of stabilizing the gas. Right, because the evaporation rate sort of as a negative feedback can depend very strongly on the number of atoms and keep it more tightly constrained. That should also show up in fluctuations. So you can have also a system which is at the threshold for this runaway condition, and by chance it can lose a few more atoms and then kind of fall off a cliff, or by chance happen to not lose or have a more efficient moment in evaporation where very high energy atoms are lost. And that would kind of push it into the runaway threshold. Yeah. I think we haven't touched that boundary. I think mostly we're studying gases where they all achieve this runaway condition. So it's easy not to get to that runaway. We can probably make it happen. It's just not what the first set of data looked at.
Can I ask a question here since nobody asking? Yeah, I was wondering, like, I mean, maybe it's a little bit simple. So, like, for the first experiment you're doing in the flat band, are you believing like you're able to do some kind of transport experiment similar to what people have been done with like bilayer graphing things? Like, or what's the similarity or difference you think like you have here?
Well, I would put this in the category of transport because we are studying the transport effects of band structure. We're studying how fast particles move within a lattice, and we're finding that interaction effects cause the atoms to move. So you have a flat band. In the absence of interactions, everything's stuck. But once you get the atoms to interact, they actually sort of accelerate and leave. So that's an interesting transport effect. To study effects like in graphene, well, again, we're working with bosons and not with fermions. So there is going to be some modification. And I would say, like other experiments where people have, probed band structure effects, maybe not the implication of band structure on a gas of fermions, but rather the band structure, let's say, at linear crossings and the pi phase shift that you get when you go around a Dirac cone. That's all stuff that I think is approachable in our experiment. And then I wanted to emphasize this sort of, I think, really interesting topic in its own right, which is all of this is a single particle description. And, we're sort of in a mean field regime because of this lattice of tubes. That's one regime in which to study it. But also in the more interacting regime, it's an active question in condensed matter physics as well. Like, when do the predictions of single particle band structure dictate what the many body system does? Very often the answer is it's a pretty good match. But what's really interesting is when it's a bad match. And so a kind of studying that boundary is going to be interesting.
maybe also relating to what you already mentioned, like the Bose-Fermi nature. I guess in condensed matter systems, like we're interested in in electrons, fermions. Now you study bosons. Like how, like, do you already like have some anticipation of what the differences would be, and how does it relate, for example, also, I guess, like to excitons in semiconductors, where you actually would have bosons that fill up a quasi-particle band structure?
I don't have a strong answer to that. I haven't thought about it deeply. I would guess, yes, there ought to be, especially in systems where you can create a large non-equilibrium population of excitons, maybe a coherent exciton wave, thinking about the exciton condensation type experiments. Yeah, that would be actually a pretty close analogy to what we're studying. But I don't really know much about sort of collective effects in exciton systems to say anything real solid about that. I mean, we've been in the process for a long time, but we are in the process of putting fermions into this experiment. So maybe those of you that are only interested in fermions, I'll have something interesting to say on that sometime soon also.
Are there more questions?
Can I ask a technical question? In the first part of the talk, you mentioned in the external setup, you mentioned something like the 1-3 interferometer. Could you comment on that?
Yeah, hold on, let's get there. Yeah, I'll say a couple of things about that. All right, so yeah, so we create two triangular lattices. There's the lattice formed by this 532 nanometer light. So that's a triangular lattice, just 3 beams intersecting. And then there's another triangular lattice formed by this 1064 pair of beams. The 532 nanometer light doesn't interfere with a 1064 nanometer light. So there doesn't have to be phase coherence or frequency coherence between these two beams necessarily. Okay, but what's really important to us is what is the position of, let's say, the potential maxima of the 532 net lattice versus the 1064 lattice. And the specific overlap between them can give us the kagome lattice or other lattice geometries. So we need to be able to stabilize that as well. And what that boils down to is interferometrically stabilizing the interference pattern from each pair of these beams, both in the green and in the red, and making sure that the green and red light have the same interference positions. And so the way we do that is we take light that passed through the cell, or maybe we take light before it passed through the cell, and we interfere both the green beams and measure their phase, and also the red beams and measure their phase. And by stabilizing that phase difference, if I assume that this path length is constant, and I guess this path length is constant, then the stable interference that I create on this face of the beam splitter translates in space to a specific location inside the glass cell where those phases are also equal. It turns out that I don't have to be so good at my optical engineering, because if this mirror moves, it'll move both the green light and the red light by the same displacement. And so after stabilization, all that will happen is that the overall lattice will move a little bit, but it will still have the same structure. So as long as these paths don't have time varying differences in the path length for the two beams, we should be okay. That turns out to be a pretty robustly maintained condition. And in fact, we also deliberately add, let's say, either a glass plate, or now what we do is we actively vary the phase of this interference in order to deliberately vary the interference pattern that the atoms see. So we need to create that kind of interference stability for all 3 beams. And we do so by separately having an interferometer that stabilizes this beam pair and this beam pair and their interference positions. And then separately another interferometer that samples this beam and samples this beam, I just don't show it, and stabilizes those ones. And then a recent upgrade we've made, which you might find curious, is if you look at the interference phase on this beam splitter, you get a measure of cosine of the phase. But if you want to stabilize the phase to any arbitrary value, you need to know both its cosine and its sine value. So we need an interferometer that will measure both the cosine phase and the sine of the phase simultaneously. We can then process those two measurements and put that phase difference at any value between 0 and 2 pi that we want, because then cosine and sine are uniquely defined. And the way we do that is now on one of these beam paths, we put in a quarter wave plate. And we have interferometers for two separate polarizations. And now one interferometer measures cosine, the other one sine. We multiply the cosine signal by a sine of phi, multiply the sine signal by cosine of phi, add the two, demodulate, and now that gives us an interference signal which I can use in real-time feedback to stabilize anywhere that I want. It's a pretty sweet technique, and we've used it, let's say, to take the kagome lattice and now actually move it, in some trajectory in space while it remains in the kagome configuration. So that's going to open up a lot of cool experiments. We just finally got that to work.
Yeah, thank you very much.
Sure.
Are there more questions? Okay, so let's all thank Dan again for a very nice talk. I would also like to point out that there are still two slots. Like if you want to discuss in more detail with Dan in the afternoon, you can put your name on the list that was sent out in the invitation. Yes, so if you want to do that, you can just do that now. I'll send out a Zoom link to make that possible. Next week, we'll have Wasim Barker speaking, so hope to see you there. Thanks.